Hello everyone, in this video we will be exploring propositional logic and logical equivalences. We will start by defining what is propositional logic is and its role in reasoning. And next we will see the concept of propositions and truth values, after which we will discuss the power of logical connectives in forming complex statements. And then we will see the purpose of truth tables in logic, and then we will understand the order in which the logical operations are evaluated. And once this is done, we will learn the outcomes of logical expressions, that is the tautology, contradiction, and contingency. And next we will delve into the concept of logical equivalences. In that we will see the fundamental laws that underpin the logical reasoning, also the duality in logical operations. And finally we will tackle the challenging questions from Part A and Part B of November-December 2022 University exam. First, propositional logic. But before we dive into the details, let's start with a basic understanding of what is logic is. Logic is the study of principles and techniques of reasoning. It's a discipline that helps us make sense of the world by analyzing arguments and drawing conclusions based on sound principles. In simple terms, it is a study of how to think clearly and make good decisions. Propositional logic is often called as sentential logic or propositional calculus, which is a branch of logic that deals with simple statements or propositions. To be simple, propositional logic, which is a branch of mathematical logic, and it's all about studying the relationship between propositions. But what are propositions? Propositions are statements that can be either true or false. These statements can be as simple as the sky is blue or 2 plus 2 equals 4, or more complex like if it rains, then the ground will be wet. So why does propositional logic matter? It is a powerful tool for representing and reasoning about knowledge, and it finds applications in diverse fields including artificial intelligence, digital circuit design, and philosophy. So propositional logic helps us to analyze, represent, and reason about the statements that can be either true or false. Next, we move on and understand propositions and truth values. Propositions are statements or declarative sentences that convey information and can be either true or false. They are the building blocks of logic and reasoning. These are the statements that express a fact, condition, or assertion. It is a type of declarative sentence that can be evaluated as either true or false, but not both simultaneously. And this distinction between truth values is the fundamental characteristics of propositions. Propositions are commonly denoted using lowercase letters such as P, Q, R, S, or T. These letters represent specific statements or conditions that can be evaluated for their truth values. The variables P, Q, R, S, or T are often referred to as Boolean variables or logic variables. And these variables serve as a placeholder for propositions and allow us to work with symbolic representation of statements in logical expressions. Propositions and their notation is essential in logic, which will enable us to construct the logical expressions and evaluate their truth values, also perform various operations to analyze and reason about the complex statements. Let's see some sentences which are propositions. See the first sentence. Socrates was a Greek philosopher. This is a proposition because it is a declarative sentence that can be evaluated as either true or false based on historical facts. It represents a factual claim. And next, 3 plus 4 equals 5. This is also a proposition. It's a mathematical statement, and its truth value can be evaluated as false because 3 plus 4 equals 7, not 5. And next, if 1 equals 2, then roses are red. This statement is proposition. It is a conditional statement that can be evaluated as true or false. In this case, it's true if the hypothetical condition 1 equals 2 were true, then the consequent roses are red would follow. Let's see some sentences which are non-propositions. Close the door. This is a comment or imperative sentence, which is not a declarative statement. And next we have the sentence, the movie Inception is the best film ever made. In this sentence, the statement about the movie being the best film ever made is an expression of personal opinion and subjective judgment. So it cannot be definitely classified as true or false, thus making it as a non-proposition. And next, what is my line? This is an interrogative or question, not a declarative statement. And we have one more example. 1 plus 1 equals 0, and the moon is made up of green cheese. This is not a proposition because it combines two distinct statements with and. In first part, 1 plus 1 equals 0 is a proposition which is false. But the second part, the moon is made of green cheese, is a separate statement and cannot be definitely classified as true or false in the context of logic. Propositions can be simple or complex. Simple propositions are atomic, representing a single statement. Simple propositions are often composed of subject and predicate, where the subject refers to something and the predicate provides the information about that subject. For example, the sun rises in the east is a simple proposition because it conveys a single statement. And next we have complex propositions. Complex propositions are formed by combining multiple simple propositions or other complex propositions using logical connectives. Logical connectives such as and, or, not allow us to create more intricate statements. Logical connectives are also called as logical operators or logical symbols, which are fundamental elements in propositional logic and predicate logic. And here is an example for complex proposition. And you can see this complex proposition that combines three simple propositions, that is P, Q, R, using if-then structure. Let's break it down. Here the variables P, Q and R are the placeholders to represent the proposition in the example. P is representing the statement, it's raining, and Q represents I have an umbrella, and R is representing I will stay dry. It's raining is a simple proposition representing the statement about the weather. I have an umbrella is another simple proposition indicating whether you possess an umbrella. I will stay dry is the final simple proposition stating the desired outcome. And we can express the complex proposition using the logical connectives. The conjunction and is represented by the logical operator and this symbol is pronounced as and. It represents the logical conjunction, which means it combines two propositions and is true only when both the propositions are true. P and Q represents the condition, it's raining and I have an umbrella. P and Q is true only when both P and Q are true. The conditional if then is represented by the logical operator implies. P and Q implies R represents the statement, if it's raining and I have an umbrella, then I will stay dry. So P and Q implies R is true unless P and Q are true while R is false. Now let's see the truth table for the logical expression P and Q implies R. P, Q and R represents the possible truth values for three propositions. P and Q represents the result of logical AND operation between the propositions P and Q. P and Q implies R represents the result of implication operation, that is if then, between P and Q and R. The columns P, Q, R represents the possible truth values for propositions P, Q and R. Each row in the table represents the different combination of truth values for these propositions. Next, P and Q column. This column represents the result of logical AND operation between P and Q. If both P and Q are true, then P and Q is true, otherwise it's false. And next we have P and Q implies R. This column represents the result of implication operation between P and Q and R. It follows the if-then logic. If P and Q is true and R is true, then P and Q implies R is also true. If P and Q is true and R is false, then P and Q implies R is false. If P and Q is false, then P and Q implies R is considered true. Here it doesn't matter whether R is true or false. That is, the truth and falsity of R does not impact the overall truth value of the conditional statement and the conjunction is false. You will find more detailed explanation of this concept as we move forward. Next we have truth values. Truth values in propositional logic is used to determine the validity of the statement. They are represented by the truth values true and false. And statements are formed using propositional variables and logical connectives. In propositional logic, the truth values are typically binary, meaning that they can have one of two possible values. True, this truth value represents that the proposition is true or correct. It signifies that the statement is true or the condition described by the proposition is satisfied. Next, false, and this value represents the proposition is false or incorrect. That is, it signifies that the statement is false or the condition described by the proposition is not satisfied. So the propositions are the statements that can be evaluated as either true or false, and truth values are the possible outcomes of this evaluation. Now let's move on and understand the logical connectives and their role in combining propositions. Logical connectives are also known as logical operators or logical symbols, which are fundamental components of propositional logic and predicate logic. They are used to combine and modify propositions to create more complex statements. Here is a list of common logical connectives along with their names, connective words, and symbols. First we have negation. The connective name is negation and connective word is not, and symbol we have not or tilde. In some programming languages, a single quote is used to represent negation. We may also use hyphen or dash to represent negation. And next we have conjunction. The connective word is and the symbol is wedge or caret. Disjunction. The connective word is or and symbol is V-shaped symbol. And next we have conditional or implication connective. The connective word is if then. The symbol is right pointing arrow or double right pointing arrow. And at last we have biconditional connective. The connective word is if and only if. The symbol is double-headed arrow and double right pointing arrow with a bar. So far we have discussed the logical connectives. Now let's see the truth tables. Truth table is a way of representing the possible truth values of logical propositions. It shows all possible combination of input values and their corresponding output values in logical expression. And now let's see the components in the context of truth table. In truth table, we have input propositions, also called as variables, column headers, rows, output column, and logical operators. And this is an example for truth table with labeled components. First, input variables. These are the variables or propositions you want to evaluate in your logical expression. Input propositions can be represented by letters, and it can take on either true or false. The top row of the truth table contains the column headers. These column headers correspond to input propositions, logical operators, or intermediate expressions in your logical statement. Each row in the truth table represents a specific combination of truth values for the input propositions. The output column displays the result of truth values or the outcomes of the logical expression for each row. If your logical expression involves logical operators such as and, or, not, implication, or biconditional, you may have additional columns in the truth table to show the intermediate results of these operations. In this example, P and Q are the input propositions or variables. P and Q, P or Q, and not P are the columns representing the logical operators. Each row represents the different combination of truth values for P and Q. The truth value in P and Q, P or Q, and not P columns represents the outcomes of these logical operations for each row. Let's delve deeper into the explanation of these truth tables for common logical connectors. First, we have negation. It is a logical not operation represented as not P. It will negate or flips the truth value of the input proposition. If P is true, then not P is false, and vice versa. That is, it inverts the truth value. Next, conjunction. It is a logical AND operation. It is represented as P and Q. The result P and Q is true only when both P and Q are true. If either P or Q or both is false, then P and Q becomes false. Disjunction. It is logical OR operation. It is represented as P or Q. The result P or Q is true if either P is true or Q is true, or both if P and Q are true. It's only false when both P and Q are false. This operation returns true if any of the conditions are met. Next up, we have conditional. It is logical implication represented as P implies Q. It works like an if-then statement. It's like saying if P is true, then Q is also true. It can be read as if P, then Q. In this context, P represents the hypothesis or premise of the implication. Q represents the conclusion, which is the statement that follows if the premise P is true. It means if P is true, then Q must also be true for the implication to be considered true. If P is true and Q is false, then the implication is false. If P is false or both P and Q are true, then the implication is true. P implies Q is true when P is false, regardless of whether Q is true or false. Also when both P and Q are true. The implication is false only when P is true and Q is false. And next we have biconditional, and it is represented as if and only if symbol. It can be read as P is true if and only if Q is true, or P is equivalent to Q, or P is true precisely when Q is true. It is abbreviated as IFF. This connective signifies that the two propositions P and Q are equivalent in the truth value, meaning that they are both either true or both false for the biconditional to be true. P is equivalent to Q is true if both P and Q have the same truth value. That is either both true or both false. It's false if P is true and Q is false, or if P is false and Q is true. From an implication, we can form three new implications. There is converse, inverse, and contrapositive. We know that P implies Q means if P is true, then Q must also be true. If P is false, Q can be either true or false, and it will not affect the truth of the implication. This statement is often expressed in terms of conditional statement. The converse is the reverse of an implication. That is, the converse statement switch the position of original premise P and the conclusion Q. To be simple, in implication, if P is true, then Q is also true. Whereas in converse, if Q is true, then P is true. So the converse simply reverses the direction of original statement. Next, the inverse. The inverse of implication means you negate both premise P and conclusion Q of the original statement. In implication, if P is true, then Q must also be true. Whereas the inverse statement states that if P is false, then Q must also be false. And next up we have contrapositive. To create the contrapositive, we negate both the conclusion Q and the premise P of the original implication and then switch their positions. So in implication, if P is true, then Q is also true. Whereas in contrapositive, if Q is false, then P is false. And this truth table illustrates how these logical relationships relates to each other and how they are satisfied or not satisfied under different combinations of truth values for P and Q. And you can see the implication is true when P is false or when both P and Q are true. It is false only when P is true and Q is false. The converse is true when P is true or when both P and Q are true. It's false only when Q is true and P is false. The inverse is true when P is false or when both P and Q are false. It's false only when P is true and Q is false. The contrapositive is true when Q is false or when both P and Q are false. It is false only when Q is true and P is false. And next we have order of precedence. To evaluate complex logical expressions, you must know the order of precedence of logical operators. And what is order of precedence? Order of precedence is a sequence in which the logical operations are performed. It's a fundamental concept in logic, ensuring consistent evaluation and avoiding ambiguity. Typically, order of precedence is defined separately for mathematics and logic, and they both have different set of operators. Here is how they would be typically categorized. The mathematical order of precedence is also known as order of operations. The acronym BODMAS or PEMDAS can be a helpful mnemonic to remember the order. It's not necessary to know the details of mathematical order of precedence unless your study involves a specific application that bridges both mathematical and logical context. To evaluate complex logical expressions, you must know the order of precedence in logical operators. We will now delve into the logical order of precedence, which is a fundamental concept in propositional logic. In logical expressions, order of precedence determines the sequence in which the logical operators are evaluated. There are three key principles in understanding how logical operators are evaluated. First, parentheses. Parentheses are used to group parts of an expression and are evaluated first. So any content within them will take the precedence over the other operators. And this allows you to explicitly control the order of evaluation in logical expressions. Next up, we have order of precedence. When no parentheses are present, operators with higher precedence are evaluated first. In logical expression, the standard order of precedence is often from highest to lowest. The negation operator negates the truth value of proposition, and it has the highest precedence. The conjunction operator combines two propositions and returns true only if both are true. It has higher precedence than disjunction, implication, and biconditional. After conjunction, we have disjunction operator. It combines two propositions and returns true if at least one of them is true. Next, implication. Implication occupies a pivotal position. It's a bridge between disjunction and biconditional. Implication serves as a conditional link, ensuring second condition follows the first. And at last we have biconditional. Biconditional is positioned at the fifth and final level. It symbolizes a strict equivalence, meaning that both conditions must be either true or false for the entire statement to be true. So understanding the specific position of these operators in the hierarchy is the key to mastering logical expressions. And note that operators with higher precedence are evaluated before the lower precedence unless overridden by the parenthesis. And next we have equal precedence. Equal precedence means that some logical operators share the same level of importance in the hierarchy. That is, when we have operators of equal precedence such as two conjunction or disjunction operators in a row, a specific rule comes into play. This rule dictates that operators of the same level of precedence are processed from left to right. In other words, they are applied in the order in which they appear in the expression, that is, proceeding from left to right. For example, take this expression A and B and C. In this expression, we have two conjunction operators in a row. According to the equal precedence rule, A and B is evaluated first and then the result is combined with C. Now let's move on and understand the concepts tautology, contradiction, and contingency. And we will be covering two categories: truth value concepts and logical validity concepts. The tautology, contradiction, and contingency are truth value concepts, whereas valid, invalid, falsifiable, unfalsifiable, satisfiable, and unsatisfiable are logical validity concepts. Truth value concepts are related to the truth or falsity of statements or propositions. They focus on whether a statement is true or false under different conditions. On the other hand, the logical validity concepts are related to the structure and reasoning within arguments. They see if an argument makes sense without worrying about whether it is talking about true things or not. First, we will see the truth value concepts. Tautology is defined as a propositional formula that is true under any possible interpretation. It is a statement that is true no matter how you look at it or interpret it. It is always true, no exceptions. For example, the sun will rise tomorrow or it won't. This statement is a tautology because it is always true. It doesn't matter what the circumstances are, it is a statement of certainty. Now let's prove P or not P is a tautology. Look at this truth table. Here P represents a statement or a variable. Not P represents the negation of P. P or not P represents the logical expression P or not P. As you can see, the result of the expression P or not P is always true regardless of the truth value of P. And this illustrates that P or not P is a tautology, meaning that it is always true. A compound proposition will be known as a tautology if and only if all possible truth values of propositional variables contain only true. A contradiction is a statement or a proposition that is always false, meaning it cannot be true under any circumstances or in any interpretation. Now consider this logical expression, not P or not P. And this expression is always false regardless of the truth value of P. This confirms the expression is contradiction because the statement is always false. So a compound proposition will be known as a contradiction if and only if all possible truth value of propositional variables only contain false. Contingency is a proposition or a statement that can be true or false depending on the specific circumstances. It is a statement that is neither tautology nor contradiction and can be true or false based on a specific truth value assigned to its components. And here is the truth table for contingency. P and Q are propositional variables and is a logical operator. P and Q is true when both P and Q are true, but it is false when at least one of them is false. It is a contingent statement because it is not always true or always false. Its truth value depends on the specific truth values of P and Q. A compound proposition will be known as contingency if and only if the proposition is neither contradiction nor tautology, which means all possible truth values of propositional variables will contain both false and true. It is a statement that is neither tautology nor contradiction and can be true or false based on a specific truth value assigned to its components. And here is the truth table for contingency. P and Q are propositional variables and is a logical operator. P and Q is true when both P and Q are true, but it is false when at least one of them is false. It is a contingent statement because it is not always true or always false. Its truth value depends on the specific truth values of P and Q. A compound proposition will be known as contingency if and only if the proposition is neither contradiction nor tautology, which means all possible truth values of propositional variables will contain both false and true. In the truth table of contingency, the last column has true and false. A statement or a proposition is said to be valid if it is always true. P and Q are the propositional variables. Not P represents negation of P. Not Q represents negation of Q. P or not P represents the law of excluded middle for P. Q or not Q represents the law of excluded middle for Q. P or not P and Q or not Q represents the logical expression. As you can see, the result of the entire expression is always true, making it as a tautology. So a compound proposition will be known as a valid proposition if and only if the proposition is a tautology. In the truth table of the valid, the last column contains only truth value. Invalid proposition refers to a statement that is not always true. In other words, it is not a tautology. Look at this expression. Let's make the truth table for this invalid proposition. Here we have P and Q or not P and not Q. And this represents the entire compound proposition. And you can see the result of the compound proposition in the last column, in which we have true in first and fourth rows, but not always true, that making it as invalid. A compound proposition will be known as an invalid proposition if and only if this proposition is not a tautology. In the truth table of invalid, the last column either has only false or both true and false. Falsifiable is a statement or a proposition that can be proven false or shown to be incorrect through evidence, observation or testing. Look at the truth table. Here we have P and Q or not P. And this expression is falsifiable because there is a combination of truth values that makes the entire expression false, such as when P is true and Q is false. A compound proposition will be known as falsifiable if and only if some values of propositional variables can make the false value. In the truth table of falsifiable, the last column can have either false or both true and false. Unfalsifiable is a statement or a proposition that cannot be proven false or shown to be incorrect. Here is an example of a simple logical expression that could be considered unfalsifiable. In this case, P or not P is always true regardless of the value of P. So, a compound proposition will be known as unfalsifiable if and only if any value of propositional variables cannot make the false value. In the truth table of unfalsifiable, the last column can contain only true value. A satisfiable is a statement or a proposition that can be made true by choosing the right values for its parts. And we have the logical proposition P or Q and not P. And the truth table shows that the assignments of the truth values for P and Q in the third row that makes the entire proposition true, which makes it satisfiable proposition. A compound proposition will be known as satisfiable if and only if some values of the proposition variables can make the truth value. In the truth table of satisfiable, the last column can have either true or both true and false. And finally, we have unsatisfiable. Unsatisfiable is a logical expression that cannot be made true. Look at this logical expression P and Q and not P. And you can see for all the possible combinations of truth values for P and Q, the entire expression is always false and never true. So a compound proposition will be known as unsatisfiable if and only if any value of the propositional variable cannot make the truth value. In the truth table of the unsatisfiable, the last column can have only false. Here are these logical concepts explained in simple terms. Contradictions are always falsifiable and invalid. You can prove them false, but you can't make them true. Contingencies are always falsifiable and invalid. You can prove them false, but you can't make them true. Tautologies are always unfalsifiable and valid. You can't prove them false and they are always true. Tautologies are always satisfiable as well, but you can't make all satisfiable statements into tautologies. Contingencies are always satisfiable, but you can't make all satisfiable statements into contingencies. Contradictions are always unsatisfiable, and you can turn unsatisfiable statement into contradictions. Now let's move on and understand the logical equivalences. Logical equivalences are statements that indicate that two propositions are true under the same condition and can be expressed using various propositions and connectives. When two propositions are logically equivalent, it means that their truth values are same under all possible interpretation and they can be used interchangeably in logical reasoning. And we denote the logical equivalence using the symbol triple bar or tribar. Not tribar is used to denote the non-equivalence or negation of logical equivalence. Look at an example of two logically equivalent expressions. In the truth table, you can see that the truth values of two expressions are same for all possible combinations of P and Q. This means that not P and Q and not P or not Q are logically equivalent. Let's determine if two logical expressions are not logically equivalent. As you can see, P and Q, not P or not Q have different truth values. Specifically, when P is true, Q is false, the statement P and Q is false, but not P or not Q is true. Therefore, P and Q and not P or not Q are not equivalent. Now let's move on and understand a set of fundamental rules and principles that govern the manipulation and simplification of logical propositions. These laws provide a systematic framework for working with logical statements, helping to analyze, simplify, and reason about them. Idempotent laws, identity laws, inverse laws, implication converse laws, associative laws, absorption laws, De Morgan's laws, distributive laws, domination laws, involution laws or double negation laws, contrapositive laws, commutative laws, negation laws, and finally we have reductio ad absurdum law. Let's explore these laws in detail. First, idempotent law. The idempotent law refers to a specific property of logical operators in which we apply the same operator to the proposition multiple times results in same proposition as the original. The idempotent law is defined for both logical conjunction and logical disjunction. The idempotent law for logical conjunction states that combining a proposition with itself using the AND operator results in same proposition. And you can see P and P is defined as P. This means that if a proposition P is true, then P and P is also true. If P is false, then P and P is false. In other words, the result of conjunction is unaffected by repeating the same proposition. Similarly, the idempotent law for logical disjunction states that combining a proposition with itself using the OR operator results in same proposition. Q or Q is defined as Q. If a proposition Q is true, then Q or Q is true. If Q is false, then Q or Q is false. Like in the case of conjunction, the result of disjunction is unaffected by repeating the same proposition. And next up we have identity laws. There are two identity laws in propositional logic. First, we will see the identity law for conjunction. P and T equals P. This law states that if you combine a proposition P with true T using the AND operator, the result is always P. And next we have P and F equals F. Similarly, if you combine a proposition P with false F using the AND operator, the result is always false. Next up we have identity law for disjunction. P or T equals T. This law states that if you combine a proposition P with true T using the OR operator, the result is always true. P or F equals P. If you combine a proposition P with false F using the OR operator, the result is always P. The identity law for conjunction states that when a proposition is combined with true T using the AND operator, the result is always the original proposition. And when it is combined with false F, the result is always false. The identity law for disjunction states that when a proposition is combined with true T using the OR operator, the result is always true. And when it is combined with false F, the result is always the original proposition. And next we have inverse law. P and not P is defined as false. This statement confirms the law of non-contradiction, which means the conjunction of the proposition P and its negation is always equivalent to false. It reflects the idea that a proposition and its negation cannot both be true simultaneously. Next, P or not P is defined true. This statement expresses the law of excluded middle. It states that the disjunction of a proposition P and its negation is always equivalent to true. It signifies that every proposition is either true or false with no other possibilities. Next up, we have implication conversion law. It demonstrates the equivalence between the conditional statements P implies Q and a disjunction involving the negation of antecedent not P and consequent Q. Mathematically, it can be expressed as P implies Q is defined as not P or Q. Here is how it works. P implies Q is the original conditional statement, which means if P, then Q. And not P represents the negation of antecedent not P, meaning that not P or Q is a disjunction that combines the negation of antecedent not P and the consequent Q, meaning either not P or Q. The implication conversion law tells us these two expressions are logically equivalent. In other words, the conditional statement P implies Q is equivalent to the disjunction not P or Q. Next up, we have associative laws. These laws describes how the grouping of proposition with the same logical operator does not affect the overall truth value. We have two associative laws. P and Q and R is defined as P and Q and R. This law states the conjunction of three propositions, and when we group them as either P and Q and R or P and Q and R results the same truth value. The grouping of parentheses can be changed without affecting the outcome. And next we have P or Q or R is defined as P or Q or R. This law states that the disjunction of three propositions where you group them as either P or Q or R or P or Q or R results the same truth value. The grouping of parentheses can be changed without affecting the outcome. And here is the truth table for associative law for conjunction. In the columns P and Q and R and P and Q and R represents the truth value of the expression on the left and right sides of the associative law for the conjunction. And they have the same truth value for all possible combinations of P, Q and R. The columns P R, Q R R and P R Q or R represents the truth value of the expression left and right sides of the associative law for disjunction. And here you can see the expressions on the left and right sides for the both associative law have the same truth value. Next, absorption laws. These laws describes how certain combination of logical operations simplify to a single operation. There are two absorption laws, one for conjunction and one for disjunction. P and P or Q is defined as P. This law states that the conjunction of the proposition P with the distinction of P and Q is equivalent to just P. In other words, if P is true, then P and P or Q is true. And if P is false, then P and P or Q is false. And next we have P or P and Q is defined as P. This law states that the disjunction of proposition P with the conjunction of P and Q is equivalent to just P. In other words, if P is true, then P or P and Q is true. If P is false, then P or P and Q is false. And you can see both the absorption laws are equivalent to P. De Morgan's laws are two important principles in propositional logic that describe the relationship between logical negation and the logical operations of conjunction and disjunction. There are two De Morgan's laws. Not P and Q is defined as not P or not Q. This law states that the negation of conjunction of two propositions P and Q is equivalent to the disjunction of the negations of P and Q. In other words, not P and Q is equivalent to not P or not Q. And next we have not P or Q is defined as not P and not Q. This law states that the negation of disjunction of two propositions P and Q is equivalent to the conjunction of the negation of P and Q. In other words, not P or Q is equivalent to not P and not Q. And here is the truth table for De Morgan's law for negation of a conjunction. And you can see the columns not P and Q and not P or not Q represents the application of De Morgan's law for negation of a conjunction. And here is the truth table for De Morgan's law for negation of a disjunction. The columns not P or Q and not P and not Q represents the application of De Morgan's law for negation of a disjunction. And they allow us to relate the negations of conjunctions and disjunctions to the disjunctions and conjunctions of negations respectively. Next, distributive laws. The distributive laws in propositional logic describes how logical operations interact when one operation distributes over another. There are two distributive laws. P and Q or R is defined as P and Q or P and R. This law states that the conjunction of the proposition P with the disjunction of Q and R is equivalent to the disjunction of the conjunction of the P and Q with the conjunction of P and R. And next we have P or Q and R is defined as P or Q and P or R. This law states that the disjunction of the proposition P with the conjunction of Q and R is equivalent to the conjunction of the disjunction of P and Q with the disjunction of P and R. And here is the truth table for distributive law for conjunction over disjunction. And this is the truth table for distributive law for disjunction over conjunction. And you can see they describe how the logical expressions can be distributed over each other while preserving the truth value of the expression. And next up we have domination laws. They describe the behavior of the logical operations in relation to certain propositions. P and T is defined as P. This law states that the conjunction of the proposition P with the true proposition T is equivalent to P. In other words, when you combine a proposition with true using AND, the result is the original proposition. And next we have P or F is defined as P. This law states that the disjunction of the proposition P with the false proposition F is equivalent to P. When you combine a proposition with false using OR, the result is the original proposition. And here is the truth table for domination law for conjunction and disjunction. The domination laws are important for simplifying the logical expressions and are often used to eliminate the unnecessary terms. They reflect the idea that the presence of a true proposition in a conjunction or the presence of a false proposition in the disjunction does not alter the truth value of the original proposition. And next we have involution law. The involution law is also known as double negation law. It deals with the negation of negated proposition. And this law states that the double negation of a proposition is equivalent to the original proposition. Mathematically, the involution law can be expressed as not P is defined as P. And this law tells us that if you negate the proposition P and then negate the result of that negation, it is equivalent to simply P itself. And here is the truth table for involution law. Not P represents the negation of P, that is the application of double negation law. The column P represents the simplified result, showing that not P is equivalent to P for all possible truth values of P. The contrapositive law describes the relationship between the conditional statement and its contrapositive. This law states that the conditional statement and its contrapositive are logically equivalent. Mathematically, the contrapositive law can be expressed as P implies Q is defined as not Q implies not P. This law tells us the conditional statement if P then Q is logically equivalent to its contrapositive, which is if not Q then not P. In other words, if the conditional statement is true, then its contrapositive is also true. And if the conditional statement is false, then its contrapositive is also false. The column P implies Q represents the truth value of the conditional statement if P then Q. The column not Q implies not P represents the truth value of the contrapositive statement if not Q then not P. The truth table shows that the conditional statement is equivalent to the contrapositive for all possible combinations of truth values. And next up we have commutative law. This law describes how the order of proposition in certain logical operations does not affect the truth value of overall expression. There are two commutative laws. First we have P and Q is defined as Q and P. This law states that the conjunction of the two propositions P and Q is equivalent to the conjunction of Q and P. In other words, the order of proposition does not affect the result when using AND. And next we have P or Q is defined as Q or P. This law states that the disjunction of two propositions P and Q is equivalent to the disjunction of Q and P. That is, the order of proposition does not affect the result when using OR. On left we have the truth table for commutative law for conjunction. On right we have the truth table for commutative law for disjunction. And you can see the order of propositions does not affect the truth value of the expression when using AND or OR, confirming the commutative laws. Next, negation laws. There are two negation laws. Negation of implication law or material conditional law and negation of reverse implication law. Not P implies Q is defined as P and not Q. This law states that the negation of an implication P implies Q is equivalent to the conjunction of P and negation of Q. In other words, not if P then Q is equivalent to P and not Q. And next we have negation of reverse implication law. Not Q implies P is defined as not P and Q. This law states that the negation of a reverse implication Q implies P is equivalent to the conjunction of negation of P and Q. In other words, not if Q then P is equivalent to not P and Q. And here is the truth table for negation of implication law. And you can see the truth values of not P implies Q and P and not Q are same in all cases. And here is the truth table for negation of reverse implication law. The truth values of not Q implies P and not P and Q are same in all cases. In both cases, the logical equivalences hold and the given expression is valid. And finally, we have reductio ad absurdum law. Reductio ad absurdum is not a set of laws, but rather a type of logical argument or method of reasoning. It is a Latin term that means reduction to absurdity. It is a technique used in logic and mathematics to demonstrate the falsity of a statement or hypothesis by showing that it leads to absurd or contradictory conclusions. P implies Q is defined as P and not Q implies false. Now let's prove the equivalence between the left hand side and right hand side of the given expression. Now start from left hand side. There is P implies Q. This is the standard conditional statement which is equivalent to its contrapositive. So P implies Q is equivalent to not Q implies not P. Now let's work on right hand side. On right hand side we have P and not Q implies false. We can use the implication law. There is P implies Q is equivalent to not P or Q. Now rewrite P and not Q implies false as not P and not Q are false. Now apply De Morgan's law to the negation of the conjunction. So we get not P or Q or F. Since not P and not Q is equivalent to not P or Q. So this is valid transformation. Now we have both LHS and RHS in similar form. There is P implies Q is equivalent to not Q implies not P. Similarly, P and not Q implies false is equivalent to not P or Q or false. And here is the truth table. And you can see the left hand side and right hand side expressions have the same truth value for all possible combinations of P, Q and F. Now let's move on and understand duality principle. It is a principle that allows you to transform a logical statement about conjunction and disjunction into an equivalent statement with operators interchanged. The principle of duality can be defined as: let S and T be the statements that contain no logical connectives other than and or. If S and T are logically equivalent, then the dual statements S and T will also be logically equivalent. Let's break down the statements. S is logically equivalent to T. This part indicates the original statements S and T are logically equivalent, meaning that they have the same truth value in all cases. S dash is equivalent to T dash. This part states that the dual statements of S and T, which are obtained by interchanging the logical AND with logical OR and vice versa, will also be logically equivalent. S and T are the original statements. S dash and T dash are dual statements. In propositional logic, the principle of duality states that for any given statement that is true, its dual statement is also true. Now let's see how to construct the dual statement. The dual statement is constructed by interchanging the logical operations and elements. And specifically it is done in three ways. Firstly, the logical AND is interchanged with logical OR and vice versa. And secondly, the universal set is interchanged with null set and vice versa. And finally, true is interchanged with false and vice versa. Now let's see how the interchange works in detail. And here is an example. The original statement is P and Q and the dual statement is P or Q. So if you have a statement that involves logical AND and its dual statement, you can replace AND with OR and vice versa. In some contexts, the principle of duality is applied to set theory. In this case, you can interchange the universal set, which is represented as U or omega, with the null set, which is represented as empty set, and vice versa. And you can also simply replace the true value with false and vice versa. In propositional logic and duality, you treat the true and false as abstract truth value, not the statements about the real world. Here it doesn't necessarily reflect the real world facts about the sky being blue or not. It's about the logical relationship between the original statement and its dual. Take for an example, we start with two statements, that is S and T. And these statements are constructed using logical AND logical OR. To find the dual statements of S and T, you interchange the logical and logical OR operator and negate the variables. This process is called duality transformation. In this example, S and T are the original statements. S dash and T dash are dual statements of S and T respectively. So if S and T are equivalent statements, their duals S dash and T dash will also be equivalent. And so far we have seen the basics of propositional logic. Now let's solve the university questions. Prove that P implies P or Q is a tautology. To prove this expression, we can use the logical equivalences or truth table. We know that tautology is a statement that is true for all possible truth values of its variables. In this case, we have two variables P and Q. So we will consider all the possible combinations of truth values for P and Q and see the expression is always true. And here is the truth table. The column P and Q represents the possible truth value for the variables P and Q. The column P or Q represents the result of logical OR operation between P and Q. The column P implies P or Q represents the final result of the expression P implies P or Q. And you can see that every combination of truth values of P and Q, the expression P implies P or Q evaluates to true. And this confirms the expression is tautology because it is always true. Now let's use the logical equivalence to prove this expression. First, let's delve into our expression, that is P implies P or Q. The arrow symbol stands for logical implication, often read as if then. It indicates that if P is true, then P or Q is true. In simple terms, this symbol establishes a relationship between two statements with one statement leading to the truth of the other. We need to demonstrate that this relationship is consistent regardless of the values P and Q. And next, we need to apply implication. To achieve this, we start by using the equivalence of implication, which enable us to rewrite P implies P or Q as not P or P or Q. This transformation is pivotal because it simplifies the expression and opens the door for the further analysis. In next step, we apply the associative property. Now we are at the step where we apply the associative property of logical OR. This property allows us to rearrange the terms with logical OR operation, essentially regrouping the elements without changing the logical meaning. In this step, we regroup not P or P, and the final expression will be not P or P or Q. To achieve this, we first regroup the terms with the inner set of parentheses, which is P or Q. And the magic happens with the associative property. It enables us to shift the parentheses leading to the expression not P or P or Q. This rearrangement does not change the logical relationship of the terms. It simply helps us to simplify the expression for the next step of our proof. Our next step involves introducing the law of excluded middle, a fundamental principle in logic. That is the law of negation and law of excluded middle. It states that P or not P is always true. In our expression, this law simplifies not P or P to true. Finally, we utilize the identity property of logical OR, which states that P or T is always equal to P. On applying this property, we further simplify our expression from T or Q to ultimate conclusion T, that is true. And this step cements our proof, confirming that the expression P implies P or Q is indeed a tautology. Let's see one more university question, which is part B from November-December 2022. Show not P and Q and not P and not Q are logically equivalent without using the truth tables. Let's break down the statements. On left hand side we have not P and not P and not Q. On the other side we have not P and not Q. We need to show both the expressions are logically equivalent. Let's start with the given expression not P and not P and Q. Now apply the distributive law to the inner part of the expression, which will allow us to distribute the negation across the conjunction. So we can rewrite the above expression as not P or not P and Q. Apply the De Morgan's law to not P and Q part. And this law states that not P and Q is equivalent to not P or not Q. Now the above expression becomes not P or not Q. And next we apply the associative law, which allows you to rearrange the order of OR operations. So the above expression becomes not P or not Q. Next we apply the negation law to this part, that is not P or P. This law states that not P or P is equivalent to true. So the above expression becomes true or not Q. Now apply the identity law to the part true or not Q. This law states that true or Q is equivalent to true. And when you have true combined with any other statement using the OR operator, the result is always true. In this case, the true is combined with not q using or, so the result is true. We have shown that not Pn, not P and Q is true. Now consider the expression not P and not Q. This is already in simplified form. In this expression we have conjunctions. The truth value of the entire expression will only be true if both conjuncts are true. In other words, for the second expression to be true, both not P and not Q must be true. Now we can see both expressions have the same truth value. Therefore, they are logically equivalent.